Let's look at that problem that you voted off the island. We have these two metal plates, capacitor plates if you will, and they're hooked to a battery. Now, by convention, by agreement by people that lived before we did, the symbol here represents a positive terminal, the long line, and a negative terminal. And that battery, it turns out, is a really, really big one you don't want to take on an airplane. It's thick, 6,000 volts, if you'll believe it. Yeah, costs a lot. Now, what that battery does is it charges up this plate positive, the one that's hooked to the positive terminal, this plate negative. It does that by stealing electrons from this plate and putting it over on that plate so that it becomes very negative. Everywhere I took an electron from, I left a positive proton naked behind. Now that's going to set up an E field between the plates that is uniform. And we know the magnitude of that E field is given by this formula. And I could use that formula to figure out the E field if I knew what the sigma was. If I knew what the total charge was, if I knew what the size of the plates were, I could do that. But I don't. So I use the fact that this plate is 80 centimeters from that plate. And I use the ED equation. Now folks, don't ever use the ED equation without using indices. If this is the voltage, if 6,000 is the number of volts between the negative and the positive plate, then that means this distance has to be the distance from the negative to the positive plate. So I would put 6,000 volts is equal to E times 0.8 meters, and that's going to give me an E of 7,500 volts per meter, and that's the same as 7,500 newtons for each coulomb. And so the electric field is everywhere going to point the same direction as the field lines. Now, in this problem, we drill a hole through the positive plate and we insert the barrel of an electron gun, whatever that looks like in your mind. And that gun fires electrons, negative electrons, at some initial velocity that we're looking for. Now, the way we're going to find that initial velocity is we know that the electrons always stop right here at point A. And so that means I'm turning kinetic energy into electric potential energy. Now, how many volts is it going to take to stop that electron? Tell your neighbor.
39,000.
Okay. What it's going to take to stop that electron is a voltage from the positive plate to the negative plate. No, from the positive plate to point A. Now, if the voltage difference from the positive plate to the negative plate is a negative 6,000 volts, right? If it's from negative to positive, I'm increasing my voltage. If I'm going from positive to negative, I'm decreasing my voltage. How many volts am I going to change if I don't go all the way to the negative plate? I only go halfway there. I only go to A. Negative 3,000. Okay? Remember, voltage is how much Verk I would have to do to take 1 coulomb and push it from some location to some location. If I go from the negative plate to the positive plate, I have to do 6,000 joules of Verk. But if I only go halfway, I only have to do 3,000 joules of Verk. Okay? And if I'm going the other way, well, a positive charge wants to fly that way, so I'm doing negative Verk. And if I only go halfway across, I'm only doing half as much. So it takes a voltage difference of negative 3,000 to stop this thing. So let's use our energy conservation. The change in kinetic energy as this electron goes from the positive plate to A is equal to the change in electric potential energy as the electron goes from the positive plate to A, with a minus sign. There's going to be 4 minus signs in this equation. Each of them have a different meaning, and each of them is critical. This minus sign is those 2 buckets, one filling and one emptying. It's the zero-sum game minus sign, where I have to get my kinetic energy from somewhere. Now, this is going to be kinetic energy final. That's going to be at point A, minus kinetic energy initial. That's going to be at the positive plate. That's going to equal the minus sign times the test charge. That's going to be an electron, times the change in voltage from the positive plate to A. Well, when it gets to A, it stops. So that's 0. So what I'm going to get here is minus 1/2 the mass of the electron times the velocity at the positive plate squared. That's the kinetic energy at the positive plate. I bring down this minus sign. It's an electron, so I have minus 1.6 times 10 to the minus 19 coulombs. The change in voltage from the plus plate to A is a negative 3,000 volts. Now a volt is just a fancy way of saying joule per each coulomb. So the coulombs cancel. I've got joules on the right, I've got energy or joules on the left. Now on the left I have 1 minus sign. On the right I have 1, 2, 3 minus signs. Well, 3 minus signs is equal to 1 minus sign. 3 left is equal to a right, but 3 minus signs is equal to 1 minus sign. So I've got negative on the left, negative on the right. It works. Now I just plug in my values. I can get rid of that minus sign if I get rid of those 3. This is going to be the mass of an electron. I'm looking for this. And what I get is a speed at the positive plate of 3.2 times 10 to the 7th meters per second. About 1/10 of the speed of light. Okay? Now, this minus sign came from the fact that we were slowing down to rest. This minus sign came from the zero-sum game. This minus sign came from the fact that we had a negative electron. And this minus sign came from the fact that we were going away from the positive plate towards the negative plate, hence a decrease in voltage. All of those minus signs are critical, and all of them mean something a little different. Okay? See if your neighbor got that problem right.
This is like on the gas. I was actually really lucky. I just watched the lines already. I did this yesterday. No.
Okay. Question?
Did I just talk about?
The N equation is not going to tell you the sign of your voltage difference. You're going to always have to use the fact, am I going away from the positive plate towards the negative plate, or am I going away from the negative plate towards the positive plate? But the N equation just can't give you that plus or minus sign there. So when I use the N equation, I'm using absolute values. Good point. Now the last part of this problem asks, well, what if I took these plates and I took the plate on the right and I moved it over to point A and I fired the electron gun just like I did before, same initial speed? Would the electron hit the other plate? And the answer is not with it hooked to that battery. That battery is going to keep the voltage between the plates from negative plate to positive plate 6,000 volts. Well, it only takes minus 3,000 volts to stop that electron, and that means no matter where you put the plates, the electron's going to stop dead set in the middle of the plates. Now, that's only because I've got a battery hooked to it. If instead I remove the battery after I charged it up, then it would be the electric field that stays constant. And then, by moving the plates half as far apart, I would cut the voltage by half, down to 3,000, and sure enough, the electron would hit the other plate. But as long as I've got that battery there, it's going to make sure that there's 6,000 volts between the plates. How does it do that? By moving charge. If I put the plates half as far apart, well, in order for me to still have 6,000 volts there, to still have to do 6,000 joules of air, I must have twice the strength of electric field. It would double the electric field. And now the electron would be fighting a field that was twice as strong. It would stop at a distance that was half as far. It would still stop halfway between the plates. Does that make sense? Oh, I hope it does. I hope it will by the time you come back from spring break. Let's talk about why we want our lightning rods to be sharp. If I have a piece of metal, and that metal has a part that is fairly sharp and a part that is not. Well, I know that it's a metal, so that means the electric field inside of the metal must be 0. Now, if the electric field inside is 0, that means I can move a test charge anywhere I want, and I don't have to fight a field. I don't have to do Varric. And so that means everywhere inside that metal and on the surface of the metal is the same voltage. Now, that means the surface of the metal is an equipotential surface. I know that field lines are always perpendicular to an equipotential surface. Okay? Now, the fact that these field lines are perpendicular to the surface is everything. That's the key. Okay? Because here, perpendicular to the surface is pretty darn parallel. But here, perpendicular to the surface causes them to spread out. And it's that spreading out that's key. If I say that metal all has to have the same voltage, let's say relative to some 0 point, it's 50 volts, okay? What that means is that relative to some 0 point, let's say the voltage is 0 right there. If relative to that 0 point, that metal is all at 50 volts, that means that if I reach into my pocket and take out a 1 coulomb, I got to do 50 joules of Varric to take this coulomb over and put it on the metal. And we learned last time it doesn't matter which path I take. Now let's think about two possible paths. One possible path is I start here at 0, and I just come in near the pointy end. Okay? Now the fact that these spread out means that I got a strong field and a really, really weak field. Okay? So this is like doing work in the British system at their universities. They have no homework. They have no quizzes. You don't have to come to lecture. Everything is based on your final exam. So you can just go and drink all semester long. You can just partay, and what happens at the end? You pay the piper. You got to do 50 joules of air to get from there to there. I wasn't doing hardly any work because these field lines were far apart. Now I got to work like a bugger. That means I'm really fighting a huge electric field. Now if I do it on the American plan, the American plan is you start here, you bring the 1 coulomb, and you bring it up this way. I gotta work, 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 I gotta work. All semester long. Okay? If I have to work all the way up here, I'm not fighting a very strong field. So the field's going to be very greatest right there by the point. Now, fields are caused by charge. And so that means if the E field is strongest near that point, the charge is clumped near that point. Now you remember last day I had a pinwheel with very sharp points. When I dumped electrons on that pinwheel with the Wimhurst machine, all of a sudden it started hissing and the pinwheel started turning. Well, that hissing was electrons being thrown off of the pinwheel by the huge electric field near the point. Okay? That's why we have sharp lightning rods. I'm going to show you a video here. Now, this video, it involves a Tobler-Holtz machine, which is like a Wimhurst machine. It works on a slightly different principle, but this thing is gorgeous. It's at the University of Washington. I used to walk past it every week. It's made out of tiger oak, and the front is just a very heavy leaded glass. And etched into that leaded glass is a staff with 2 serpents coming up it. And this, of course, is the symbol of dentistry. Okay? This came out of a dental office in 1890, and it creates huge lightning bolts. You can only imagine what they might be using it for in a dental office in 1890.
Demonstrate how a lightning rod works. One side, we'll use this model house and a high voltage electrostatic generator to demonstrate how a lightning rod works. One side of the generator is connected to a metal ball inside the chimney. This sharp rod is also electrically connected to the same side of the generator. The other end of the generator is hooked to this copper sphere, which simulates a charged cloud in the atmosphere. When the generator is cranked with the lightning rod down, large bolts strike the chimney.
Or your mouth.
When the lightning rod is raised, the bolts stop.
Listen. Do you hear the hissing?
When the lightning rod is lowered, the large bolts resume.
Okay, now, as you have a thunderstorm, the wind, just like rubbing rubber rod with cat fur charges it, the wind causes a friction that's going to charge up the ground, charge up the clouds. and set up a charge separation. Now, somewhere, that is going to spark. Now, the whole point of a lightning rod is not to say, come hit my house. It's to take the charge that's building up on your house and throw it off your house so that your house isn't charged. The reason you have a lightning rod is not so that it will hit your house, but so it will hit your neighbor's house. Okay, you want to essentially neutralize your house. Now, if you can't get the charge off of your house fast enough, then it still can strike your house. But that gives a second function of the lightning rod. If it does perchance hit your house, the most easy, most natural way for that charge to get to ground is through the lightning rod, which is connected with a great big heavy cable down to ground. Okay? But the key is that you have to have that lightning rod very, very sharp so the electric field near it is strong enough to throw charge up into the air and neutralize your house. Now, I have here a little video. Okay. So what we have here is super slow motion picture of lightning. Now I'm gonna pause that. In my textbook, not the one we use for this class, but we use for the conceptual physics class, we claim that lightning cascades from the ground up, that the actual flow of charge happens from the ground up. We put that in the book because one of our colleagues, Dick Rabisco, was an expert on lightning, and he claimed that was true. For years and years and years, I thought he was just pulling my leg and that we had something wrong in our book. I felt very bad about that. And then I saw this video, and watch how the ionized path is getting set up from the cloud to ground. But once that path touches the ground, watch the cascade. Now, it happened from the ground up.
Wow.
I was right. Not me, but Dick Rabisco. Okay, so let's start it back here. It's reaching down for the ground. It's ionizing a path. The first path to get fully ionized, that's where it blasts.
So it's not necessarily the best path, just the first path?
Just the first path. Okay. When it comes to lightning, the first path is the best path, by definition. Okay. Now, there's some lightning. Here's some lightning that's caused by the violence of a volcanic eruption on Iceland. Okay. We have enough time to talk about capacitance. Now, we're going to charge up these capacitors, and I'll talk about what that means in just a moment. This capacitor we're going to charge up to 2,000 volts. That's going to be right here. Okay. And this capacitor bank here is the one that's deadly. And this is how I lost my hearing, this one here. And
Should I be covering my ears here?
what's that?
Should I be covering my ears right now?
It's not going to go off for a while, so you're going to be fine. Actually, last period, it was very disappointing. We came in and we found there was a bunch of oil leaking out of this one here, and the boom that we had was about half as loud as it normally was. And I suspect that someone, last time they used it, may have damaged this capacitor here, and so instead of two in parallel, we just have one in parallel. I truly apologize. But we're going to raise that to 3,000 volts, and it's going to take a while. It didn't take nearly as long as it normally does in the last class, and that's why I suspect that one of them is damaged. But for people in the front row to watch this gauge, I'm now using the top scale, and when it gets near 3, you gotta wave and get my attention and get me to turn this off, because if it gets past 3, we destroy the other one as well. Okay, so let's talk about capacitance. Capacitance is just what it sounds like. How much can it hold? If we're talking about the capacitance of your gas tank, the question arises, how much gas can it hold before what? Okay? How much gas before it leaks out, before it gushes out the hole and lands on your shoes? Okay? Now, if I have a conductor, I can store not gas on it, but charge. It can be a repository, a bank that can hold charge. And the question is, how much charge can it hold? Well, how much charge can it hold until what? Until lightning strikes and destroys the room? That's not very useful. So instead, we ask, how much charge can this conductor hold until we change its voltage by 1 volt relative to some reference point? By 1 volt. Now, here's a simple example. There's the operational definition of capacitance. If you set delta V equal to 1, you see that the capacitance C is equal to the charge that is stored when the voltage is equal to 1. Suppose I were to dump 6 coulombs onto this conductor, and I find that it raises the voltage by 3 volts. Well, that would mean that the capacitance of that would be 6 over 3, or 2 coulombs for each volt. Coulomb per volt we call a farad, to honor Michael Faraday. Okay? Now, we're up to 2,000 volts. Now, typically, we don't have one conductor, but we have 2 conductors. And instead of just charging one, we charge both of them. But we charge one positive and one negative. And we do that by typically hooking it to some sort of battery. Now, if I went down and bought a 1 volt battery, that would be cheap. If I hooked it to those metal balls, that would ensure that the voltage difference between A and B would have to be 1 volt. What that means, physically, is that I would have to do 1 joule of Verk for each 1 coulomb that I move from A to B. Well, how does the battery do that? Well, it does it by charging up the conductors. It steals electrons from this one and dumps it onto that one. That sets up an electric field that's pointing this way, and that's what I'm fighting to do my Verk. That's why I have to do 1 joule of Verk. Now, you see that the charge on the 2 conductors, when you add it up, is always 0. The only way I got an electron over here was to leave a naked proton over there. So the total charge stored in this set of conductors is 0. But when we define the capacitance, we only take one of the charges, the positive charge, to put into this equation. And that's because only one of these charges is useful for running your household appliances. When you hook this thing up to something, the electron, yes?
No, it's
Close.
about.
It's just making me notice.
2,800 volts,
There's an amp or before 3,000.
2,900 volts. Yeah. 2,850 volts. Oh, we're so close to breakdown. Let's turn that off. Okay. Now, worry, I'm not gonna do anything. Just calm yourself, I'm still lecturing. But nobody get out of your seat and go touch that, okay? That would be bad. And especially don't touch it with your tongue. Okay. Now, I have here a Bimhurst machine connected to a bank of what are called Leyden jars. Now, Leyden jars are just primitive capacitors, the type that Ben Franklin used. Now, Ben used an old canning jar, a glass jar, and he put a metal foil on the inside and a metal foil on the outside. The glass jar was just to keep the two electrically separated so that the charge couldn't short right from one to the other. Now, what I have here is a set of 4 Leyden jars. In the inside I have aluminum foil, and all of that foil is connected to this structure here, electrically. On the outside I have aluminum foil, and all of that is connected at the bottom to aluminum foil, and that aluminum foil comes right up here to there. Now the Bimhurst machine you've seen before, it separates charge. It puts negative charge over here, leaving positive charge there when I turn the wheel. We talked about the fact that it takes 30,000 volts to throw a spark through 1 centimeter of dry air. So what I'm doing is I'm storing enough charge to build up the voltage of this thing to 30,000 volts. Now, if I connect these bars electrically to the inside and the outside capacitor bank of that Leyden jar bank, and I'm going to move that over there, and I'm going to leave these leads here about 1 centimeter apart again. What I've just done is I've increased the capacitance, the storage ability of this device. I've got a lot more room to store charge. Before what? Before it raises 1 volt. I still have to raise it 30,000 volts to get it to arc across. So tell your neighbor what's going to happen as I turn this crank. I have to store a whole lot more charge before I get up to 30,000 volts. It's going to take forever for me to get up to 30,000 volts. But once I get to 30,000 volts, once I throw that spark, it's all going. Okay? All the charge that I've been storing up is going to, yeah, that's what I mean. That's what I'm talking about. Okay? So I get a much bigger spark. Now, the most common type of capacitor is a parallel plate capacitor where you have 2 sheets parallel to each other. And yet most capacitors look like tin cans. And if you open them up, what you find, I've got an example here, you find 2 metal sheets that have been rolled up over and over again like toilet paper. And between the 2 metal sheets, you have a sheet of paper that is coated in oil. That's going to be your insulator that separates the 2 conductors. And then you just roll it up so that it can fit inside of a cylindrical package. Now this particular capacitor is broken. Someone brought it up to a much higher voltage than it wanted to be. And you can see that the paper that's supposed to separate the 2 conducting sheets is all pockmarked. And that's because the charge actually sparked right through the paper. Now, I used to just pass this around the class and you can unroll it and play with it. And then we found that the stuff is toxic. Those students died. But you can pass it around. It's in a jar that protects you. Okay. Now, if we move an amount of charge equal to sigma times the area, Sigma is the surface charge density, how much charge there is per unit of area, times the area of the plates. I get one plate positive and one plate negative. That's going to generate an electric field between those plates. It's given by that formula that we found last day. That's just sigma over epsilon naught. The same sigma that we have in Q. Now, that's going to create a voltage difference between the plates given by the ED equation. Now, if I take this value of E and I plug it in there, I find the voltage difference between the plates to be, there's my E, sigma over epsilon, and there's my D. Well, now if I take my operational definition of capacitance, I put the charge in there, I put the voltage in there, and I divide. Well, there's the charge, there's 1 over the voltage, and you can see that the sigma cancels out. It's independent of the charge that's stored. All it depends on is the area of the plates, the conducting plates. The bigger the area, the more you can store, more charge you can store, because it can spread out. The smaller the distance between the plates, the more you can store. That doesn't seem logical, unless you remember that capacitance is how much you can store before what? Well, before you get up to 1 volt. Well, if those plates are really, really close, I don't have to fight the field between them very far. And so I have to have a whole lot of charge before I get up to 1 volt. The problem is, if you put those sheets really, really close together, they're more likely to arc across through whatever you've got between them. So you have to be careful how small you get that D. Now, when I was alive, we had capacitors that were measured in nanofarads or microfarads. And if you opened up a computer or something, well, there's a lot of my life we didn't have computers. Can you believe that? We didn't have computers. We had the abacus. Anyway, I knew how to use a slide rule. I was really good at it. Anyway, an old motherboard, you look at it and it's got a bunch of these little flat pancake looking brown things all over it. Well, those were little tiny capacitors that would store charge for when you needed a burst of current. And lately we've been able to get high-tech dielectrics that allow us to get capacitance up to 1 farad. Okay, if you look at any capacitor, you'll see 2 numbers on it. The capacitance in farads, and that's just coulombs per volt, and the breakdown voltage, meaning don't put more volts across it than this or you're going to destroy it. Now, if I use the operational definition, I can solve for how much charge can be stored in that capacitor. The maximum amount of charge is stored when I put the maximum number of volts across it. If this capacitance is 3 coulombs of charge for each volt, and I raise it up 20 volts, each of those volts I'm going to store 3 coulombs. That's going to give me 60 coulombs. Now, Greg, what are you trying to pull? 1 coulomb would destroy this campus. 60 coulombs destroy the world. Well, the capacitor always holds the same amount of positive charge as negative charge. On the positive plate, I'd have 60 positive coulombs. On the negative plate, I'd have 60 negative coulombs. That can is always electrically neutral. It has no net charge. But I can move the electrons off of the negative plate over to the positive plate, and in the process of doing it, I can run, well, I could run a computer. Okay? Now, let's blow up some capacitors. The first one I'm going to blow is a 2 microfarad capacitor. It stores, if you use that formula, 0.004 coulombs. And I think you'll agree that, no, come on. Now don't you feel silly? Okay. Now, this one has 100 times the capacitance, except I think one of them's broken, so I think maybe it just has 50 times the capacitance. At any rate, now you should. Chat YouTube. Can you imagine when it was twice that loud? Here's the thing. If I had charged that up and then just taken it right back to the demo room and put it on the shelf, left it there for 5 years, and then just told a grad student, hey, would you go get me that capacitor, man? Just go get it. They go down, they grab it, they're just, pow, they're dead. Okay? This is the most dangerous thing in your demo storage room. And so you always want to check, when you approach one of these, you approach it with a paddle. And you make sure that it's got the positive and negative terminals sorted out. And then it's safe. Don't ever just grab one of these things without making sure it's safe first. Now, this last one is, I saved the best for last. This is one of those new tech ones with the dielectric in it that's 1 farad. And if I bring it up to 5 volts, this is 1 coulomb per volt, times 5 volts is 5 coulombs. So, and this has a very definite positive and negative because of the dielectric. And I've set this so that it will only go up to 5 volts. Okay? And so let's get this disconnected. Okay. Are you ready? Everyone ready? Oh, come on, people, it's 5 volt. It tingles, but it doesn't hurt me. Okay? And the key is, yes, this does store more than 10 times the charge. But it's not the charge that does damage. Remember, energy is the capacity to do damage, and these capacitors not only store charge, they store energy as well. Now, if I want to calculate the energy stored in a capacitor, I could follow student 1, which is never a good idea. I know that the electric potential energy is given by the charge multiplied by the voltage difference, so I just multiply those two together. And student 2 is more right. That formula would give the change in potential energy of a test charge moving from one plate to the other. To find the total energy stored in the capacitor, I'd have to add up all the variables necessary to charge it up from 0. So far, so good. I would probably have to use calculus. When they say that, you know they're not using their imagination. That part's wrong. If you take the total charge and you multiply it by the average voltage that you have to cross, and that would, if I'm going from 0 to V max, that's just half V max. If I replace the Q with C delta V, you see that it depends on the voltage squared. And that's key. Voltage squared. If I go back to this example, I have 400 joules of energy in the big guy, and I released it all at once with the metal paddle. Here, I've got more charge, but I don't have nearly as much energy, and I released it slowly through my tongue that has more resistance. It tingles, but it doesn't do any damage to me. Okay? So it's the energy that does damage. Folks, I hope that you have a wonderful spring break. I hope you use sunscreen. I hope you come back safe. We love you all.
Great. Can you go back one slide? Can you go back one slide?